Hello all, I'm Siddharth Kaul and I welcome you to Edupedia world. In this video, we are going to deep dive into character class. Strings and characters are correlated. Using character class, we also create strings. So strings are nothing but arrays of characters joined together. A string can be created by writing characters within an enclosed single quotation mark. This is aptly represented in line 1 where I have created a string hello world enclosed in single quotation. If we are going to have a single quotation mark inside our text, we write two quotation marks within the string definition as done in line number 2. Here the other string variable contains the text you are right with a single quotation. This single quotation is defined with a double string quotation. This has been discussed many times before in my previous video. The base class for all the strings and character array is the character class. This can be identified by using the whos command and checking the class attribute. The myString variable shown in line 3 is a size 12 array of class character. Functions such as integer functions, especially the unsigned integer functions, convert the characters to their equivalent numeric codes. This has been demonstrated in line number 4 and 5. The myString variable containing the hello world string is converted into a numeric equivalent using the unsigned integer function, getting a numeric array with values of 72 for H, 101 for E, 108 for L, 111 for O, 44 for space, and so on. The inverse of this numeric conversion is also true. As these numbers represent certain character in character class, the character conversion of these numeric values will return us a character array. This inverse conversion is shown in line number 6 and 7. In 6, I have defined a character a numeric code in string alpha and I'm converting that to a character. So I get hello world for the equivalent numeric codes. Concatenating the string is as easy as concatenating numeric values. Okay, this is not a good line for comparison, but the procedure is the same. We can have the horizontal concatenation of strings and vertical concatenation of the strings. Shown here is a vertical concatenation. To combine string into a two-dimensional character array, we can use the methods demonstrated here. So this basically demonstrates a vertical concatenation. So we have a development underscore title where we have certain names, say Thomas Arley. Then we use semicolon, we get senior developer. Then we use semicolon, then we get software cop. So these three values says the name, the position, and the company in a vertical format. Similarly, same can be done using function character. So we have manager underscore title with the character function called, and we are creating a vertical concatenation using character. Similar to this, we have a horizontal concatenation. For this purpose, we can do horizontal concatenation as shown here. So two ways we can do. Either we use a concatenation operator, that is square bracket and comma, or we used a string catenation function as shown in the last line. So in the first half, I have used a square bracket concatenation operator to do a horizontal concatenation. So the name, title, and company will come into one single line. Similarly, in the second half, where name is my name, domain is my domain, and extension is com, I am using string catenation function to do a horizontal concatenation of name, domain, and extension with @ and dot in between. Identifying characters in a string. Matlab provides us with some functions that helps us identify what kind of characters or what kind of alphanumeric has been used in the string. So we have is character that determines whether the input is a character array or not. We have is letter that finds all the alphabetical letters in the input string. Then we have is space that finds out all the spaces in the input string. Then we have a is string prop, so find all the characters of a specific category. So shown in the example here, I'm going to identify all the spaces in the string. The string here is find the space characters in the string with spaces in between the words. So the spaces as is at words is at the position 5, 9, 15, 26, 29, and 34. So using the function isSpace, I'm going to find this location. So isSpace string will return all the places where there is a space there, and find function will return us the location where the space is located. So using this combination of these two functions, we get the location 5, 9, 15, 26, 29, and 34 where the space is located in the string. Working with space characters. Here I'm going to show how to work with spaces and what can be done with spaces in Matlab. We can create a string of spaces using the function blanks and passing the length of blanks whatever the length we want. In the first line, I have created blanks 15 with size 15. So you can see there is a 15 spaces 15 spaces size is there. So now to make this blank visible, what I have done is as enclosed it within a vertical bar. So in the second example, you can clearly see 15 spaces within this vertical bar. Now I'm going to replace the spaces from location 6 to 10 with letter A. So I'm using a location replacement like as 6 to 10 and I'm replacing it with 8. So we can clearly see the position of A's in the answer. We have 5 spaces before A's, 5 A's, and then 5 spaces after the A. Continuing with this arrangement, we can see justification of strings. Doing left justification does not delete the spaces but move the series of A's to the left, hence having 5 A's and 10 spaces, as shown in the first example. So we have S left, which is the justification of the previous string S to the left. So instead of like 5 spaces, 5 A's and then 5 spaces, we are now having 5 A's and 10 spaces. Similarly, right justification does not delete the spaces but moves it to right. So we have 10 spaces and then 5 A's. So S right is the string right justification of the string S. So as you can see, the 10 spaces have come to the left side and all the 5 A's have gone to the right side. Point to note, as already been discussed, is that spaces are not deleted, they are just rearranged. Again, continuing with the same strings of A's and spaces, we have a dblank function that truncates the trailing spaces, so we are left only with 5 spaces and 5 A's. The trail 5 spaces are erased by this function. So remember, as we know that S has 5 spaces, 5 A's and 5 spaces again. Using dblank function, we are only left with 5 spaces and 5 A's. The trailing 5 spaces have been erased. Then we have string trimming that trims or truncates all the spaces in the string, leaving us with only 5 A's. Converting to a cell array of strings. Creating strings in a regular MATLAB array requires that all strings in the array be of the same length. This often means that we have to pad blanks at the end of strings to equalize their length. However, another type of MATLAB array, the cell array, can hold different sizes and types of data in an array without padding. Cell arrays provide a more flexible way to store strings of varying length. To understand it better, let's see the code written here. Here we have three names: Bigfoot, Jack, and J. Observe how the padding has been done after Jack and J so that they match the size of Bigfoot. When the data is converted to cell string as shown using cell string function, we see that there is no padding after Jack and J. This can be verified by checking the length of J using the length function, like length of cell data for position 3, that is J, and we get a value of 3. So this shows that there is no spacing after J. We can verify this concept of padding by converting the cell structure data back to the character data. This conversion will add the spaces behind the smaller string and have their sizes match the one of the largest strings. Here in this case, the biggest string is Bigfoot with 8 characters and the smallest is J with size 3. So this conversion will add the 5 spaces behind the J, making the length of that J character to 8. This length again can be verified using the length function, and we can clearly see the length to be 8. Functions for cell arrays in strings. So There are some certain cell and cell string functions available in Matlab. We have cell string that converts a character array to cell array of strings. Then we have character functions that converts a cell array of strings to a character array. Then we have dblank function that removes the trailing blanks from a string. We have isCellString function that returns true if the passed argument is a cell array of strings. Then we have sort function that sorts elements in ascending or descending order. Then we have string catenation function that of course concatenates the string. Then we have string compare function that compares the string with each other. Formatting strings. MATLAB offers the following function that offers the capability to compose a string that includes ordinary text and data formatted to our specification. Sprintf. Sprintf is used to write formatted data to a string. Then we have fprintf that is used to write formatted data to output file or command window. There is a warning that displays the formatted data in a warning message. We have the error that displays the formatted data in an error message and then aborts. We have assert that generates an error when condition is violated. We have mException that is something that captures the error information. The syntax of each of these functions include formatting operators similar to those used by printf function in the C programming language. For example, %s tells MATLAB to interpret an input value as string, and %d means to format an integer using decimal notation. We will look into that. Here I have shown a very basic example that clears everything that I have just talked about. I am using sprintf function to print a string with combination of text, integers and floating values. So I have used input arguments of single %s, 3%d and a single %f as shown. And these 5 input arguments are followed by 5 other input arguments, one for each formatting string. So we have string bread for %s, integers of 7, 1 and 2006 for %d and a floating value of 2.49 for %.2f. When MATLAB processes the format string, it replaces each operator with one of these input values. Inserting a special character. Special characters are part of the character set, but as they cannot be entered as an ordinary text, they require a unique character sequence to represent them. The table shown here shows what character sequence to use to insert what special character. So we have single quotation mark. To insert a single quotation mark, we used single quotation marks twice. To insert a percentage character, we use percentage character twice. To insert a backslash character, we use backslash character twice. To insert an alarm, we use backslash followed by A. To insert backspace, we use backslash followed by B. To insert form feed, we use backslash followed by F. To insert a new line, we use backslash followed by N. To insert a carriage return, we use backslash followed by R. To insert a horizontal tab, we use backslash followed by T. To insert a vertical tab, we use backslash followed by V. To insert a hexadecimal number, we use backslash followed by X followed by an hexadecimal number. To insert octal number, we use backslash followed by our octal number. Input value arguments in formatting strings. There are some key points to remember for input value arguments that are being used in formatting strings. The syntax for the same is highlighted in yellow. It is a format operator immediately followed by a value. Usually each format string argument will have its own value. For the value of format string arguments, we cannot pass cell arrays or structures. If fewer formatting operators are used as shown in blue, then MATLAB reuses the operator on the additional values. The line in blue shows how the two formatting operators is used to insert 6 values into the string. So using the same %s and %d formatting operator, we have inserted 6 values of a equal to 479, b equal to 352 and c equal to 651. Sequential and numbered arguments. So what if I do not want the output string to take the data sequentially? As of now, we have placed the value arguments in the argument list sequentially. In order to have our own sequence, we can use identifier with the formatting operator. For writing identifier, we add number to each operator that identifies which value argument to replace it with. The table here shows the comparison of the default sequential order and when we order the value through an identifier. On the left, we have the normal use with sequential ordering where we don't use any identifier, just a formatting operator followed by the value argument in the sequence, like %s, 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 followed by first value, second value, and the third value. Here on the right, I have shown the use of identifier where the number 3 and a dollar sign is inserted in between the formatting string operator. So we have %$3s, %$2s, and %$1s. That says to take the third argument first, then the second argument, then the first argument. This is how we use the identifiers to create our own sequential and numbered arguments. The formatting operator. The formatting operator tells the Matlab the way to format the numeric or character value arguments and where to insert them into the strings. These operators control the notation, alignment, significant digits, field width, and other aspects of output strings. The formatting operator begins with the percentage character, which may be followed by a series of one or more numbers, characters, or symbols, each playing a role in further defining the format of the insertion value. The final entry in the single conversion character that Matlab uses to define the notation style for the inserted data. The conversion character used in Matlab are based on those used by the printf function in the C programming language. Here are the 5 ways shown. So in the first way, we are just using %f. That means we will be inserting a floating point value. Then in the second one, we have %.2f. Here .2f is the precision after the two decimal, this is precision up to the 2 decimal limits. Then we have %+.2f. This displays a positive for the numbers, floating numbers. Then we have %12.2f. This sets a width to 12 characters with the precision of 2 decimal digits. Then we have %012.2f. that replace the leading spaces with 0. So we get a number like 0000314.16 with that still with 2 decimal precision. Constructing the formatting operator. So what makes up a formatting operator? The fields that makes up a formatting operator are marked in red below. Lastmost character in this formatting operator is a conversion character that specifies the notation of the output. Then at 5 we have a subtype that specifies any non-standard types. Then at 4 we have the precision that sets the number of digits to be displayed on the right side of the decimal point or the number of significant digits to be displayed. Then at 3 we have the field width that sets the minimum number of digits to be displayed. Then at position 2 we have flags that controls the alignment, padding, and inclusion of plus or minus sign. Then at last, at the first position, we have the identifier that map the formatting operators to value input arguments. Using this identifier field when value arguments are not in a sequential order in the argument list. So one by one, we are going to look into each of these that make up a formatting operator. Conversion character. The conversion character specifies the notation of the output. It consists of a single character and appears last in the format specifier. It is the only required field of the format specifier other than the leading percentage character. So we have a specifier and we have a description. So when we use character C, that denotes a single character, D denotes decimal notation, E denotes exponential notation, capital E denotes a capital exponential notation. Then we have F that denotes fixed point notation. Then we have G that is the more compact of either E or F. Then we have O that is octal notation. Then we have S that is string of characters. Then we have U that is decimal notation. Then small x is smaller hexadecimal notation and capital X with capital hexadecimal notation. Subtype. The subtype field is a single alphabetic character that immediately precedes the conversion character. The first table shows shows the non-standard subtype specifier supported for the conversion character for octal, hexadecimal, and decimal format operators. We have B that says that data type is a double rather than an unsigned integer. For example, to print a double precision value in hexadecimal, we use a format like %bx. Then we have T, character T, that says that the data type is a float rather than an unsigned integer. To specify the number of bits for the conversion of an integer value corresponding to conversion characters like decimal, integer, octal, and hexadecimal, we have one of the subtypes as shown in table 2 at the bottom. We have L that says to use a 64-bit value for conversion, and we have H that says to use 16-bit value for a conversion. Precision in formatting operator. Precision in formatting operator is a non-negative integer that immediately follows a period. For example, the specifier %7.3f has a precision of 3. For the %g specifier, the precision indicates the number of significant digits to display. For the %f, that is floating, %e, that is exponential, the precision indicates how many digits to display to the right of the decimal point. Precision is not usually used in format specifiers for string. If you do use it on a string, and if the value of precision field is less than the number of characters in the string, then MATLAB displays only p characters of the string and truncates the rest. Field width in formatting operator. Field width is a non-negative integer that tells MATLAB the minimum number of digits or characters to use when formatting the corresponding input value. For example, the specifier %7.3f has a width of 7. Here are a couple of examples that will make this field width concept a little easier to understand. So first we have a %e where we have not specified any width. So we'll get the full width. Then we have %15e that says to have 15 digits of width in the answer. So you can say we have 7 plus 8 spaces that is equivalent to the 15 width in our answer. Then again we have %f for floating where we get an answer like 157.079, and then we have %15f that says that total field width should be 15. As there are not enough numbers to fill the field, so that field width is filled with spaces of 6. Similarly, when field width used with strings like %30s, and a string is put and the string width is not equivalent to 30s, then the number of spaces are padded to make the length as 30. Flags. We can control the output using any of these optional flag. So we have a minus sign that left justifies the converted arguments in its field. It is used like %minus 5.2d. Then we have plus signs that says to always print a sign character either plus or minus. Then we have a space that inserts a space before the value. Then we have a 0 that pads with zeros rather than spaces. Then we have a pound sign that modifies the selected numeric conversion. Let us see some example for flags. The example 1 demonstrates the right and left justification of the output. The default is the right justification. So as you can see, the default is right justification. So 1230 is right justifies automatically. To left justify, we use the minus sign. Example 1 demonstrates right and left justification of the output. The default is the right justify. As you can see, by default 12.30 is right justified. So to make it left justify, we use a minus operator before the formatting operator. Example 2 demonstrates how to display a positive sign for the positive number. The default is to omit the positive sign. So we have a plus 12.2f that says to display value with the positive sign. Example 3 demonstrates padding. Here padding to the left is done with spaces or zeros. The default is to use spaces. Field width and precision. The figure illustrates the way in which the field width and precision settings affect the output of the string formatting functions. In this, the 0 following the percentage sign in the formatting operator means to add leading zeros to the output string rather than spaces. So on the left, we have a normal string that we will be formatting. So we have the whole part that is 1, 2, 3 and the fractional part that is of 5-digit length that is of 4, 5, 6, 7, 8. Now we are going to use format operator of percentage 0 9.3f that says the width of the hole is 9 and the precision is 3. So the result has a whole number as 00123 that is extended with 0 and we have a precision of 3 that is 457. The subtractional part of the result has p digits and is rounded off. The p digit here is nothing but the precision of 3. Here are few general rules for formatting. If the precision is not defined, it defaults to 6. Second, if precision is less than the number of digits in the fractional part of the input value, then only p digits are shown to the right of the decimal point in the output and the fractional value is rounded. Third point is if precision is greater than the number of digits in the fractional part of the input value, p digits are shown to the right of the decimal points in the output and the fractional part is extended to the right with p minus f zeros. Fourth point is if the field width is not specified, it defaults to precision plus 1 plus the number of digits in the whole part of the input value. If the field width w is greater than p plus 1 plus the number of digits in the whole part of the input value, then the whole part of the output value is extended to the left with w minus n plus 1 plus p space characters or zeros, depending on whether or not the zero flag is set in the flag fields, the default flag field or not. The default is to extend the whole part of the output with space characters. String comparison. Moving to strings. There are several ways to compare strings and substrings. First, one can compare two strings or parts of two strings for equality. Second, one can compare individual characters in two strings for equality. Third is one can categorize every element within a string, determine whether each element is a character or white space. These comparison and the function that will be used can work for both character arrays and as well as cell arrays of strings. We have four functions available in Matlab to determine if the two input strings are identical. String compare determines if two strings are identical. So string compare takes string 1 and string 2 and returns 0 if they are not equal. On the left, I have shown the usage of string comparison and string and comparison. We have string 1 hello and string 2 with help. First we compare the whole strings, which obviously is not the same, so we get output as 0. Then we do comparison only till the first two characters, which is same, hence we get an output as 1. On the right we have cell arrays of string. A with words pizza, chips and candy, and A and B with words pizza, chocolate and pretzels. When we do string compare for these two cell arrays of string, we get column vector that shows 1 if the complete string at that position matches. Similarly, we do string and compare till first character and then we get a column vector 2 with two ones in it. Comparing using equality operator. We can use the Matlab relational operator with the character array in the same way we use them with numeric arrays. Here shown is an example where I have used a relational operator that is equal to compare string fate and cake. Here the output we get is an array with 1 at positions where characters are the same and 0 where they are not. All the relational operator that is less than equal to, greater than equal to compare the values of the corresponding characters. So as you can see, F and C does not match, so we get output as 0. A and A does match, so we get output as 1. T and K does not match, so we get output as 0. And E and E does match and we get output as 1. I'm going to end this video by summarizing few functions that will be used to convert number to string. Matlab provides a number of functions to do the same conversion. These are the functions using which we can convert a number to a string. So we have a character. This converts a positive integer into an equivalent character. It truncates any fractional part. Then we have integer to string that converts a positive or negative integer to a character. Say for example, we have 72 and 105, so it converts into equivalent integer character, that is 72. Then we have number to string that converts a numeric type to a character type of specified precision and format. Then we have matrix to string This converts a numeric type to a character type of the specified precision. Returning string MATLAB, returning a string MATLAB can evaluate. Then we have decimal to hex that converts a positive integer to a character type of hexadecimal base. Then we have decimal to bin that converts a positive integer to a character type of binary base. Then we have decimal to base that converts a positive integer to a character type of any base from 2 to 36. This concludes our video here on character and strings. In the next video, we are going to continue with date and time. So until then, please subscribe and thanks for watching.